The entirety of science is based on a simple assumption. If you do the same thing the same way, you will get the same result. That assumption allows us to develop theories, hypotheses, and predictive equations which guide us. And this assumption that directly connects action with result is nowhere more evident than in the science of analytical chemistry and the discipline of chromatography. Chromatography, as an analytical technique, is the most widely used methodology in analytical chemistry. The most deployed form of chromatography is high-performance liquid chromatography, or HPLC. HPLC is a powerful analytical technique used for the separation, identification, and quantitation of complex mixtures of chemicals. It is widely used in various fields, including in pharmaceutical development, pharmaceutical testing, and drug testing, in medical research, medical diagnosis, and clinical testing, in the food and beverage industry for food analysis, and in the chemical and environmental industries during environmental cleanups. In this series of videos, we will explore the fundamentals of HPLC, including its principles, components, instrumentation, and applications. First, let's take a look at some applications of HPLC. CSI, Crime Scene Investigations. The CSI dramas were a very popular franchise of television shows. CSI Las Vegas ran for 15 seasons, CSI Miami ran for 10 seasons, and CSI New York ran for 9 seasons. At their core, these shows highlighted the role that laboratory analysis played in the crime-solving process, as far as television crime dramas are concerned. Virtually all of the street drugs can be detected, identified, and quantified by high-performance liquid chromatography. One of HPLC's strengths, or differentiators, from other analytical techniques is that it works at room temperature in a solvent, where many other analytical techniques need their analytes in a gaseous state and require specific sample preparation. The more complex compounds, like drugs, rapidly degrade at high temperatures, and at that point are difficult, if not impossible, to isolate and detect. The other issue to note, which can be a plus or a minus, is that the UV detector is the default detector for HPLC. For the most part, this requires that the compound to be detected must absorb in the UV region of the spectrum. This, for the most part, requires that molecular structure of the component to be detected have conjugated pi systems. So look for those features in the molecules we present. Most will be large labile molecules with a benzene-like ring and subsequent conjugated pi systems. Drugs like cocaine, ketamine, methamphetamine, psilocybin, and rohypnol. Pharmaceutical research. In January 2023, the FDA, United States Food and Drug Administration, published the new drug therapy approvals for 2022. HPLC is used in many of the steps to discover, develop, introduce, manufacture, and distribute new drugs. These are a few of the drugs that were approved for 2022. As you examine these drug structures, be sure to note that all of these drugs are large labile compounds, susceptible to degradation under high temperature conditions, and the structures all contain conjugated pi systems. This makes HPLC the analytical method of choice. High-performance liquid chromatography plays a crucial role in the discovery of drugs by enabling the separation, identification, and quantitation of compounds within complex mixtures. HPLC is a powerful analytical technique used in the early stages of drug discovery to evaluate the properties of potential drug candidates. Here are a few of the steps in which HPLC is a core asset. Step 1. For compound screening. In the early stages of drug discovery, researchers screen large compound libraries to identify potential lead compounds with desired biological activities. HPLC is used to separate and analyze these compounds based on their physiochemical properties, such as polarity, molecular weight, and solubility. Step 2. For purification and isolation. Once lead compounds are identified, HPLC is employed for the purification and isolation of these compounds from complex mixtures. By utilizing appropriate stationary phase column packings and mobile phases, HPLC separates the desired compounds from impurities, facilitating further characterization. Step 3. For quantitative analysis. HPLC is employed to quantify the concentration of drugs or their metabolites in biological samples during preclinical and clinical studies. This information is crucial for determining the pharmacokinetics and assessing the efficacy of drug candidates. Step 4. For structure elucidation. HPLC, coupled with various detectors such as mass spectrometry, ultraviolet detectors, or fluorescence detectors, aids in the identification and structure elucidation of drug compounds. By comparing retention times, spectra, and fragmentation patterns with reference standards or databases, researchers can confirm the identity of the compounds. Step 5. For stability testing. HPLC is utilized to evaluate the stability of drug compounds under various conditions, including temperature, humidity, and exposure to light. By monitoring the degradation of compounds over time, researchers can assess their shelf life and optimize formulation strategies. And step 6. For chiral separations. Many drugs exhibit chirality, meaning they exist in different enantiomeric forms. That is, they exist as mirror image isomers. HPLC is employed for chiral separation, enabling the separation and quantitation of individual enantiomers. This is essential because enantiomers can exhibit different pharmacological activities, different metabolism rates, and different safety profiles. Overall, HPLC is an essential tool in drug discovery, offering precise and sensitive analysis of compounds, facilitating separation and purification, and providing crucial information on the characteristics and behavior of potential drug candidates. Environmental disasters. At 216 North Pleasant Drive, East Palestine, Ohio, on Friday, February 3rd, 2023, at 8:55 p.m. Eastern Standard Time, there was a train derailment. The train consisted of tanker cars carrying, reportedly, 6 chemicals. In the tanker cars were vinyl chloride, isobutylene, 2-ethylhexylacrylate, butyl acrylate, 2-butoxyethanol, and benzene. In a high-temperature environment, such as a fire, these starter chemicals can produce an almost infinite number of chemical products, most of which are not good. And while benzene is the only one of these precursor chemicals that can be easily analyzed by HPLC, a large majority of the products produced from a high-temperature environment such as this can be detected, analyzed, and quantified. This positions HPLC as a prime analytical technique for assisting in the cleanup. The basics. When we are tasked with the identification and quantitation of a chemical or series of chemicals, one of the first questions we ask ourselves is,
How can I differentiate or separate the compounds I want to identify from all the other chemicals in the sample matrix? So first, we began to look for physical or chemical differences that allow us to separate the compounds. One such difference is polarity. Let's take a look. In the separatory funnel is hexane and water. Hexane and water do not mix. They are immiscible. Water has a higher density than hexane, so hexane is on the top and water is on the bottom. Hexane is nonpolar, water is polar. In this example, polarity is about hydrogen bonding. Water is the textbook example of hydrogen bonding. The compounds that are more able to hydrogen bond in solution will be considered more polar. So water is polar, hexane is nonpolar. Look for an OH or alcohol moiety in the molecule, or an oxygen attached with a double bond that can morph to an OH under the proper acidic pH. If we pour a randomly mixed solution of polar, nonpolar, and volatile compounds into the separatory funnel, they will gradually separate. The polar compounds will go to the polar solvent, the nonpolar compounds to the nonpolar solvent, and the volatile compounds to the airspace at the top. Let's be a bit more specific and replace the anonymous bulls with specific chemical molecules. At the hexane-water interface, you will see a compound like the polar acetaminophen in the water layer and the slightly nonpolar compound fentanyl in the nonpolar layer. Moving to the nonpolar volatile layer interface, you will see the nonpolar aniline in the nonpolar layer and the more volatile pentane in the vapor above the hexane layer. At its core, chromatography is about using the difference in the physical characteristics of components in a mixture to separate, identify, and if needed, quantify the individual components. High-performance liquid chromatography, like here in the separatory funnel example, uses liquid partition coefficients to accomplish the desired separations. So you will find HPLC columns characterized as reverse phase HPLC columns and normal phase HPLC columns. The reverse phase columns are used to separate polar compounds, and the normal phase columns are used to separate nonpolar compounds.